We're going to pick up with how we can model disorder within AFLOW. This was one of the topics that Professor Cuderillo talked about in his keynote address. Again, we're going to go over some of the details, some of the technicalities, and we're going to run some of the analysis with AFLOW today. All right, let's get started. So the session earlier today, when we were talking about stability of materials, we really focused on that enthalpy term. And today, and now we're gonna really focus more on the other term, the entropy term. So first, what is disorder? Okay, so when we talk about, let's define order first. So here we have a zinc oxide crystal structure. Okay, and if you remember from my first session on VASP, we talked about the fact that because it's a crystal, there's periodicity in the system, so we can reduce this macroscopic structure down to a unit cell that repeats everywhere in space. Okay, so that reduction, that ability to reduce the unique information is implied by the fact that we have order, symmetry, and periodicity. Okay, this is really an ideal approximation. The truth is that the real world, even for crystals, there's impurities, there's defects, there's randomness, there's disorder that disrupts the ability for us to reduce this information down to this really unique unit cell, this very small unit cell. Now, there's a lot of different types of disorder, but I'm going to focus on, I'm going to talk about two today, and we're really going to focus on one. Okay, so there's one type of disorder, which is called structural disorder, and that's what characterizes glasses. Where you see here that for a crystalline variant of glass, here we have quartz, you get this regular array of atoms. The atoms are arranged in a very nice periodic structure. With glass, you lose that structural periodicity. The atoms are now positioned randomly. Okay. There's another type of disorder called chemical disorder. So typically, if we have a unit cell here, each site is uniquely occupied with one element. So, you know, here in the corners, we have zinc. And then here in the middle, we, instead of having a singular occupant, we're going to have this site partially occupied between sulfur and selenium. And there's a ratio here where we have more selenium than sulfur. Okay, and so the idea here is that these sites are characterized by two occupants or more, and that's chemical disorder. Okay, so we're really going to hone in on the chemical disorder. That's the type of the structural disorder we're going to focus on for the talk. All right, remember this picture from my talk earlier today. I talked about the enthalpy gain, this n+1 enthalpy gain, where we look at what is the enthalpy gain from going from one species to now two species. And we see that pictorially or illustrated here, where there's a gain. This mixture is lower in enthalpy than the tie line connecting the two pure phases. We can do this analysis for all of the compounds in the AFLOW database, all the binary compounds. You can do the same for the ternaries. Okay, so basically we're looking at the enthalpy gain for a compound which sits in the middle of this compositional space versus the convex hull defined only by the edges, the binaries and the unaries. We can do that analysis for all the ternaries. This is a slightly different picture than the one I showed earlier, but it shows the same information. We have the enthalpy gain as a function of the number of species. Okay, so we can see here that as we increase the number of species, the enthalpy gain goes down. Not only do we see that the enthalpy gain goes down, but there are fewer compounds that show any enthalpy gain. This has to do with this recursive stability competition concept that I referred to in the earlier session, where as we increase dimensionality, every dimension contributes more competition for where the bottom of the convex hull is. So the binary set the first stage, then the ternaries now have to compete not only with other ternaries, but with the binaries as well. The quaternaries have to compete with ternaries, quaternaries, and binaries, and so on and so forth. So you see here that the enthalpy gain, this distance on average decreases with increasing species. Okay. Now, if we compare this with the ideal disorder, this was a picture that Dr. Cuderola presented in the keynote speech. You see that entropy quickly overtakes the enthalpy gains. Okay, so this is just for the ideal entropy. This is complete disorder. We can talk about polar materials where you have a sublattice structure. We'll talk about what that looks like in a bit, but really these are these polar materials. You can isolate the disorder to particular sublattices. And so if you isolate the disorder to particular sublattices, you reduce the disorder by a species or two, but fundamentally you're going to have a crossover where the entropy is going to overtake the enthalpy. Now, why is this important? This is important because this really gives us a sense of direction for the future. As we continue to look for more multi-component systems where we can get an average, a blending, or even we can accentuate certain features with adding more and more components to our materials. As we go in the future in this direction, we have to realize that the future in this direction is going to be heavily weighted toward disordered materials. So we cannot put the blinders on, which a lot of which has been done because it's very difficult to model disorder. So in terms of computation, it's very easy to put the blinders on and ignore disorder. But if we're interested in exploring the future of this field, we really need to focus on disorder. It is unavoidable. Now, you cannot just take a postcard, like in VASP, a geometry file, and apply disorder. It's not something that can be done that way. So there are other approaches that we can take for modeling disordered materials. Broadly speaking, there are a few favorites in the literature. There are mean field approaches, which include the coherent potential approximation. You might see CPA in the literature. There's also virtual crystal approximation, VCA. Now, these approaches, they're generally single site approaches, and I mean they do different things in the method, but fundamentally what you're doing is, if you're going to have atoms that are sitting close to each other or sitting on the same site that are occupied by different occupants, fundamentally mean field approaches is going to look at some sort of averaging scheme where you turn these red and blue atoms into a purple atom. Okay, that's very similar to what, for instance, virtual crystal approximation is doing. Problem with this is that we lose some of the fundamental behavior that we expect in these materials. The fact that we have these atoms that are very different, that are going to be sitting in the same site and interacting, this is going to give way to local lattice distortions. These lattice distortions are very important in engineering applications, specifically modeling hardness, or it's going to give rise to hardness. So mean field approaches, you can see how we're going to miss some of this behavior in this modeling approach. Another approach that's very popular in the literature is called it's a supercell approach, and it's called special quasi-random structure. Generally, we're going to model our system as one singular supercell, very large supercell. It's called SQS in the literature. It's a very popular approach, and in a lot of ways has been very successful. There are some caveats that are important to know when you're modeling your system with SQS. You require a very large cell, and this cell is going to be very low in symmetry, and implicitly you're biasing your model toward an infinite temperature solution because you're choosing the most random possible configuration. We're going to focus in on this particular caveat in a few slides, but this is a very important assumption, and you need to assess whether your properties and it's whether it's a reasonable approximation to model the system as being the infinite temperature solution. Okay, so now we're going to discuss a new approach, which is called the AFLOW partial occupation algorithm, or AFLOW-POCC for short. And the idea is very simple. And I want you to focus in on the cartoon that I'm going to illustrate for you, because this is how we're going to model our systems. We have magnesium oxide. We have a powder here. You can imagine that if we had X-ray vision and we can look at the structure directly with our eyes, well, we might see something like this. Magnesium oxide has this rock solid structure. If we dope it a bit with zinc, okay, and we look at a particular part of the powder, we might still see this magnesium oxide structure with our X-ray vision. But as we continue to look around the powder, we'll see that some of the sites that were uniquely occupied with magnesium are now partially occupied with zinc. This is the chemical disorder I've been referring to. But look at the picture here. We have one picture of the rock salt magnesium oxide structure, another piece of this zinc oxide structure here, okay? And so we're gonna have these two structures that are coming in and out of focus in this cartoon. This is exactly how we're gonna model our system. We're going to model our system instead of doing it as a singular supercell. We're going to model it as an ensemble, a Boltzmann ensemble of supercells. Okay, so here we have our example disordered system. And based on the stoichiometry, I'll go into a bit of this in the next slide. We can build supercells where we have this ensemble which represents these ordered representatives. These ordered representatives are going to represent, on average, the disordered system. And the idea is that these different ordered representatives are going to exist somewhere inside this grand picture of the material which is disordered. Okay? So that's the concept. Let's focus in on the details here, because the technicalities, the devil's really in the details. This is really where it's important to understand what AFLOW-POCC is doing. So again, we're going to model our disordered system as an ensemble of ordered states. For this slide in particular, we're going to focus on how we get these individual ordered states. So we have our system here, zinc, sulfur, selenide system. It has a particular space group, which is what the structure looks like. If we look at the stoichiometry here of the disordered site, we have 0.25 sulfur, 0.75 selenium. If we create a supercell size 4, then we can represent our stoichiometry exactly in the supercell. What do I mean by that? So if I take this site and I create a supercell that's size 4, I'm now going to have, instead of one site, I'm going to have 4 sites. And if I decorate those sites with one occupant each in the ratio that I'm looking for, I will match the stoichiometry exactly. So you see, I get one site here in the yellow, I get sulfur, and I get 3 sites selenium. So overall, the supercell satisfies the stoichiometry of the original disorder system. Now, the point is that because we have disorder, there's not just one choice that I can make in how I decorate. There's actually at least 4 here. There's 3 others. So I can take this yellow site, I could put it here instead, which is what this cell looks like. I can put it on the corner here or here at the bottom. Okay, and these are all different viable decorations given the specification of the partially occupied site. So there are at least 4 here. Now, because of the structure that I have here, the space group 216, and the way I've decorated the sites, all of these decorations, the 4 different decorations, they actually turn out to be symmetrically equivalent. But the point is, you still need to do the analysis to figure out whether they are symmetrically equivalent, and you can consider them to be degenerate. Okay, so this is the slide I showed earlier was I did permutations of the sites that are allowed for a given supercell size. But it's important to realize that that box, the way I created that supercell, that's not the only way that I can create a supercell size of 4. In this case, for this particular space group, turns out that there are actually there are 7 ways that I can create the box within which I decorate the atoms, within which I put the atoms inside. So this box here, the brown, that was the supercell I showed you earlier, where if you can imagine one box being the primitive structure. So this supercell, the brown one, was the one I showed you earlier. But you can make supercells that are very skewed and diagonal, and they're going to give me different structures that I need to explore. And within each of those are the 4 different decorations. So 4 decorations each, there are 7 of these. I get 28 total ways that I can build structures that are that comply with the stoichiometry and the structure that was given by the primitive disordered structure there. So there's 28 different decorations and different permutations of the structure. And POC, the algorithm that we're discussing today, it considers all of these decorations. It's important to mention that because there are some softwares that do variations of what I'm talking about today, but for instance, they will only decorate it based on this uniform expansion supercell. They won't consider the various different supercells with different skewed with different skewed directions. And those cells were going to play a very important role in determining the energy spectrum within which we can describe the stability of disordered materials. So keep that in mind. We really need to decorate. We need to explore all the possible decorations. That's going to be something that I'll discuss in a few slides why that's important. Okay, so I discussed how we create these different ordered representatives, but how do we get the averaging? Am I going to model this so that each one of these gets an equivalent P1, P2, P3? Do they get equal probabilities, or is there going to be some weighting? The weighting is going to be associated in this algorithm with a Boltzmann weighting, and I'll talk about how we derive that. So of the 28 total structures, we can do symmetry analysis as Dr. Hicks discussed yesterday, and we see that there are 7 unique structures. Okay, for each of the 7. Each one of these has 4 degenerate structures, right? These are the different decorations that symmetrically give us the same structure. So we get a degeneracy value. That's that G1, G2, G3. So we get 7 of these degeneracies. We can take these ordered representatives. These are now perfectly ordered structures. We can plug them into VASP and get their enthalpies back, right? As I discussed earlier, treated as a black box. We can get the enthalpies for each of these 7. One of these 7 is going to be the minimum enthalpy structure for the set here. Okay, so we're going to call that one the ground state structure for the set. We're going to define our Boltzmann probabilities here. The Boltzmann probability for each one of these supercells, so this is P1, P2, P3, we're going to plug in the degeneracy values. Then we get this canonical exponential term, which is standard for Boltzmann. We take the difference of each one of these enthalpies and subtract it from the ground state structure enthalpy, okay? And we divide it by the Boltzmann constant times what looks like a temperature. It's a temperature type parameter, and it's a tuning parameter. This temperature I can tune, and it basically determines how much disorder I want to incorporate in my calculation. Let's look at some of the extremes here. If T is very close to 0, then the probabilities of all 7 of these structures is going to be practically 0 except for the ground state. So the averaging is going to be heavily skewed to the ground state structure, which is exactly what we expect when we have low temperature, the ground state structures dominate. So the properties of the disordered material are going to be heavily weighted on the ground state structure. As T approaches infinity, we're going to get a more equal probable distribution of probabilities where the weighting is really going to depend now on the degeneracies. So in some cases, you might get structures which give you degeneracies where one of them has a really large degeneracy. We'll see an example of that today, actually. But otherwise, all of the other probabilities are going to be effectively equal, but barring the degeneracy weighting. Okay, so the question now is, how do we compare this AFLOW-POCC approach, which is a supercells approach, with SQS, which is a supercell algorithm? And we need to talk about what SQS is fundamentally. So for those of you who have not studied SQS, the idea is really a generalization of the Ising model, which, if you remember from physics, is what we use to study magnetic ordering in materials, or really the phase transition between order to disorder with temperature. Okay, so what do we have here? The Ising model. We have here a term in our Hamiltonian, which associates or gives benefit to neighboring spins that are either aligned or anti-aligned, depending on whether you have a ferromagnetic or an anti-ferromagnetic material. So when we're at low temperatures, Let's assume we initialize our space all with the spins, all spins up, okay? And so all the spins have, let's work within a ferromagnetic approximation just so that it's easier to describe. But if we're in a ferromagnetic approximation, all the spins want to be aligned. So at zero temperature, they're all going to be up, okay? As we turn up the temperature, there's going to be some probability that these spins flip. And that spin flip is going to disrupt this magnetic ordering. So if we look at the average magnetization, how likely is it if we look somewhere in the material that we see that spins are correlated up? We see that there's going to be a big phase transition with temperature, where at some point we have a ferromagnetic ordered system. And then after a critical temperature, everything is random. We have a system where if you look at the neighbors, some are up and some are down. That's the idea I want you to walk away with here. If you look at a neighboring cluster of spins, if you look at the ordered range of very low temperature, they're all going to be spin up, and they want to be spin up because they get a gain in stability. That the energy is lowered if all the spins are up. Okay, but if you look at the disordered range where the temperature is high, and you look at the correlations, you could not tell me whether whether any individual site is going to be spin up or spin down because it's random. So as I shift this bubble around, you're going to see some sites are up, some sites are up or down. So you cannot predict what the site's going to be. And that is that temperature, that role that it plays in causing disorder. That's exactly what's going on with our cells here. So here are the 7 structures that I showed you earlier. For SQS, what we're doing is that we apply our easing model spin up and spin down to the various sites that are partially occupied. So we had, let's say we had magenta that was selenium and sulfur was yellow. So we're going to give spin up to the magenta and spin down to the sulfur. Okay, and we're going to analyze the correlations within these neighboring sites. So we can go throughout the entire structure and we can calculate what's called the correlation function, the structural correlation function. What does this mean? We take this bubble and we look at pairs, triplets, etc. And we analyze what the correlations are. Are they likely to be spin up? Is one going to be spin down? We do an average across that. We look at different neighbors. So we can do next nearest neighbors, so on and so forth. And we can calculate what the correlation function is for each one of these structures, each one of these 7. One of them is going to have the minimum correlation, okay, where we're really in that high disordered spectrum where we have very high temperature. So that looks like our picture where we're in a very high disorder regime where where that's what that minimum correlation number tells us. So SQS is the selection of the one structure out of all of the 28 that gives us the minimum of the correlation functions. But there's a caveat here because I told you that it's the minimum. It's not necessarily 0. In order to approach a correlation function which is close to 0, I need to build a very big structure. Okay. And so we're talking about in the literature, you might see structures that are greater than 80 atoms. I've seen 100 atoms. We're talking about big supercells. And the fact that we're choosing only one, and we're really in this picture here, means that we're focusing in on the very high disorder picture, the very high disorder regime, where really that only exists when temperature is infinite. You don't, as Dr. Crudolo talked about, you don't go from order to disorder in a snap. There is a transition. And so if we want to talk about modeling disorder in the very far end where we have an infinite temperature, very high, everything is purely random, then you would use something like SQS. But in the interim, when you're talking about finite temperatures, you're not going to have a singular representation. You need to talk about averages, ensembles, and Boltzmann averages here. Okay, so fundamentally, POC and SQS do approach the disordered structure regime, but they do it in 2 different ways. So here I have a plot of order and disorder. How am I doing? It's on 15 minutes. I have a plot here where we want to go from order to disorder. And we're looking at it as a function of size of our supercell. So how big is it? And then how many supercells do we have in our ensemble? So SQS goes at it from one end. Really, we're only ever going to have one supercell. And that supercell gets bigger and bigger and bigger as we want to get more accurate properties. That's how it approaches this disordered limit. POC comes at it from the other end. So we can make our ensemble bigger and bigger, and the cells themselves are also going to grow in size, but generally speaking, they're really growing in size of the ensemble set. So they're generally much smaller. They don't grow in size as large, as fast, but they do grow in the collection number. That's how we're going to approach the disordered limit in terms of increasing the collection number. So SQS, as I've been hinting at for a while now, it's not going to be very good as we want to model coming out of the phase transition and in finite temperatures. Okay, that transition from the precursors to the disordered system, SQS is not going to be very good for modeling it there. It's going to be really great for modeling the infinite temperature solution. What you really need is a basis or an ensemble set. And so from that perspective, POC is really a superset of SQS structures. Okay. There's a very important consideration here, and that is the practical, which is how are we going to compute the properties of these systems? We're going to do it on a cluster. And the fact that we have with SQS, we're going to have a very big structure, which of course we can parallelize across nodes, but the bigger the structure and the more nodes that I need to parallelize across, the more speed that I'm losing between the communication of the nodes. So the fact that I have smaller cells means that I can model these in parallel, one on each node. So that's going to speed up the calculation because POC is fundamentally a high throughput approach. It's something that you can parallelize much easier and therefore get the properties much faster than something like a giant SQS structure. Okay, so we are, let's see how I'm doing with time. Let's explore the online module. We'll break at noon as planned, and then we'll come back, well, noon time, Eastern Standard Time. I believe that is 1800 in Europe and in Germany. So I'm gonna stop sharing my screen. We're gonna go online and we're gonna play with the online module for the next 12 minutes or so, and then we'll break and then we'll see where we are with the exercises. So let me stop sharing my screen, and then I'm gonna share my full desktop. Okay. Everyone see my screen here?
Yes, you might want to increase font a bit.
Will do. Thank you very much. Oh, it's already enormous. Okay, so let's just make this full screen. You're gonna go to AFLOW.org. You're gonna scroll down and go to AFLOW-Online. Go to the input part car tab here, and it's actually going to give you an example part car. Okay, so the part car is a structure, is a geometry file that we've created for AFLOW. Look at part, right? Part for partial occupancy. So it's a generalization of the postcar from VASP. Okay, so let's talk about the structure here a little bit. With the postcar, remember we have the title line, we have this line here, which gives me the either the volume or the scaling factor. We have the lattice parameters. We had the number of atoms for each species, direct or Cartesian, and then we had the atom positions written in direct or Cartesian. So how do we change this for the part car? Okay, so we have two additional parameters here. These are the stoichiometric, the site and the stoichiometric errors respectively. So for right now, I'm going to make these tolerances very tight because I want to find the structure that models my stoichiometry exactly. But if you're looking at a particular phase and that phase has a very difficult, a very narrow range, or rather not a very narrow range, it has a very wide range on the phase diagram. Let's say you have a phase which spans a few different stoichiometries. you might be able to reduce down the calculation time by exploring different stoichiometries. I'll talk about that a little more in the upcoming slides, but those two tolerances are you're going to want to keep your eye if you have a broad range of stoichiometries within which you can play. Here's another difference from the postcard. Previously, we had integer numbers. We had 1, 2, 4, 5 for the number of atoms for each respective species. Now we're going to do, we're going to have a line which is going to tell me how each species occupies each of the sites, and there's going to be, now we're going to have some fractions. So we have one site here, the first site, which is fully occupied, okay, fractional number 1. The next site is going to be partially occupied, okay, 50%. This hafnium site is going to be, the next site is 50% occupied by that. And you see that we have the same duplicate site on the next line, and it's partially occupied with niobium. So that site is partially occupied 50-50 between hafnium and niobium. Okay, so you can see how that's how we construct the geometry file for AFLOW to understand to do the POC analysis. So we click that here. We're going to scroll down to the partial occupancy settings. We're first going to click the optimized H&F value. Okay, and then I'm going to hit submit. Okay, so we get a few responses here. Let's take a look at what we have. AFLOW is going to give us back the input, basically telling us that it understood the file that we provided. And you can see here that it's gonna populate all the values as it understood it. And so you're going to want to check these to make sure that you've put the values correctly and that AFLOW understood the parameters as you wanted to put them in. It's going to do some cleaning of the structure. It's going to try to extract out the parent structure. So this parent structure here is basically the backbone structure if you were to remove the partial occupant sites and replace it with a fully occupied site. So you see here we basically returns back the rock salt structure. I wouldn't worry about the redecoration. This is a technical detail, but now that it's understood these details, it's going to verbose out some of the tolerances. You see the stoichiometry tolerance, the site tolerance. We're not going to worry about that for now. Then it's going to generate a table. And this table it's going to build supercells of increasing size and see how much error there is in that representative supercell with respect to the disordered structure that we want to model. So let's look at the first line here. We're going to try to model our system as supercell size 1. So we're not going to increase our unit cell. We're going to see how well it does in modeling the disorder of the original structure. So by modeling it with a supercell size of 1, you'll see that the site is going to have there's one site that is 50-50, and so we have to make a choice. Well, either hafnium is going to have to go there or niobium is going to have to go there. And so the site error is 0.5, because the site has that particular site is now missing 50% of the occupant that we didn't choose. And the stoichiometry also has an error of 0.5, because in choosing hafnium, so now we have carbon hafnium, we've missed out 50% of the carbon hafnium niobium stoichiometry that we wanted to model originally. So you see here that the tolerance, the values of the errors are much higher than the tolerance values. So it's saying we didn't satisfy our tolerance. So we're going to go to supercell size 2. And in supercell size 2, we can now decorate one site with hafnium, one site with niobium. So we've been able to satisfy the constraints of the problem. You see that there's no site error because we were able to occupy our sites with one with niobium, one with hafnium, and the stoichiometry is satisfied because we have carbon 2, hafnium 1, niobium 1, which satisfies the disordered systems stoichiometry. So if we wanted to satisfy our constraints here, we've done it with a supercell size of 2. Okay, so that's how that works. Okay, Before we go to break, I'm going to show you the second option we have here for our web. Oh, by the way, do we have any questions? Let's see. Okay, we have a few comments. The POC module seems perfect to calculate the formation energies, but how accurate is the Boltzmann averaging performance to calculate other structural properties? For example, the by temperature. That's a great question. I'm going to talk about we've done various analyses for different properties. And I'll show you that that not only does POC do well in modeling these different properties, but as a general theory, if we increase our supercell size and we model it with a cell size that's larger than necessary, and therefore our set's going to be larger, the error is going to reduce. So as a theory, we have a way of actually getting better results. And we'll talk about that more. This is going to be after the break. But we've done that analysis for various types of systems. I'm not going to show the Dubai temperature specifically, but if Dr. Toer's there, he can send it to DOI for a publication we just had recently, where we did this analysis for certain carbides, and we do show that there's a very nice we were able to model the system well. Is there a conversion tool for example, the SIFs to part cars? Since SIFs are often when we get to, no, actually, well, I'm going to refer this question to Dr. Hicks. I don't recall, because he's the one who implemented the SIF reader. I don't recall if he's implemented it such that it will generate a part car for you. I actually believe the answer is yes, but he can verify for that for you in the chat, or if he wants to unmute. But I believe that the answer is yes, that in general, it will actually understand the disordered system. AFLOW can understand the SIFs, and then it'll spit out a part car for you.
I believe we read in the partial occupation as for building the actual part car. That is actually something that I would need to double check, because in the part car, we have those tolerance values, and I don't think that those are automatically set. Long story short, I think we are actually close to having something like that. So if we don't have it, we could probably easily implement it.
Great, great, great. And Dr. Toer put up the link there for you. So thank you very much. Okay, with 3 minutes, I'm just going to quickly show you what the other option is. So if we click, instead of optimize H&F value, I'm going to click on calculate POC supercells. I'm going to hit submit. And what you're going to see is we're going to see a lot of the same output as before. It's going to calculate what the optimized H&F value is, which is really the supercell size we need. And then what it's going to do is it's going to go ahead and calculate and determine what all the possible decorations that are needed. And it's going to do a calculation of degeneracy. So it's going to create all of the structures. So let's walk through line by line, and then we'll break for lunch. So it's going to first determine the total number of supercell decoration permutations that we have. So we have a unique count of H&F matrices of 2. So that means that there are 2 types of way that I can build that box. Remember that nice graph that I showed you with all the skewed cells? In this case, there are 2 types of supercell box shapes that I can make. And then for each one of those boxes, there are 2 ways that I can decorate the sites. I can put hafnium in one and niobium in the other, and then switch them. So I have 2 different permutations. That gives me 4 possible decoration permutations, right? Just multiply the 2 numbers together. It's going to do an analysis of these 4, which are degenerate. And what it finds is that there's 2 unique structures. The way that it does this is called the UFF energy analysis. So roughly speaking, we can plug these structures into Dr. Hicks's algorithm of Xtel Finder, and it'll tell us exactly which are unique. But when we get a lot of different decorations and permutations, this analysis is going to be a little slow. And so we do an approximation where we actually calculate, roughly speaking, the energies of these structures. We look at the atoms, the bonding. We get a rough sense of what the energies are in the structure. And then if the energies are equivalent for 2 structures, then they're considered degenerate. And this analysis is very fast. So once it determines that, it'll actually give you, these are vast postcard files. These are the ordered representative structures for that ensemble set. You can take these postcards, these geometry files, and plug them into VAST. So it gives you these structures right here. That's what the web tool does. Okay, great. Okay, so we're going to, okay, I see we have some questions here. I'm going to break for lunch. So we're going to break for lunch, and I'm just going to say that we're going to come back. We're going to come back at 1900 hours Dresden time, which is 1 o'clock Eastern Daylight Savings Time. We're going to come back after lunch or a meal or whatever, after a break, and we're going to pick up from here. So I just want to say, enjoy your lunch. Thank you very much for coming. We can stop the recording, and I'm going to answer some questions now that we're in the lunch break. Okay, so, all right, let's see what the questions are. Not sure if my question makes sense, but did you verify your methodology in a force field where you can calculate the energy for a large cell? I'm not sure I understand the question. But I think what you mean to say is that we verify the methodology in a force field where you can calculate the energy for a large cell. I don't quite understand what you mean. So the methodology has been verified in terms of checking how accurate the properties are with respect to the disordered system when we actually experimentally verify that. As a theory, I'm not sure that we've done the sort of verification that you're asking for, but it would be interesting to learn more about what verification you're asking for. Okay. But if you would like it, if you want to unmute or if you want to verify your question in the chat, feel free to do so. No, really, if the energy of the disordered system is reproducible. The energy, listen, the energy of the system, the energy is not really, remember, energy is not a quantity that you can really measure. It's differences in energy. And so the energy of the disordered system is not necessarily something that we verify. What we can verify are the properties of the system, something like band gap, something like the density of states, something like the Debye temperature. These are properties which we verified against experimental materials, what the literature tells us, and we do get very good reproducibility of the results. And not only that, but it has excellent predictive power. So we make the predictions first. When we'll talk about this study, this is a study that Dr. Carrillo talked about in his keynote speech, but we'll emphasize it more in this talk. We were able to predict materials a priori. Okay. So yeah, absolutely, no problem. Thank you for coming. Okay, so that's I think that's the last question we have here. All right, I will be around. We can I'll be around, and oh, I misspelled it. Was indeed great. Beautiful. Thank you, Dr. Hicks. Dr. Hicks was very able to verify that when a SIF does have partial occupancy, the part car is returned. So that's excellent. You know, I don't know if you have an example, but maybe we can play with it with AFLOW. If you have an example SIF file, we can show you what that looks like. Okay, great. Thank you for your time, and we'll break for lunch. Feel free to post in the chat. I'll be here answering questions. Hello, everyone. We'll give everyone a few minutes to get back. Well, we'll do a minute or two, and then we'll pick up with the POC lecture shortly. Dr. Frederick, can you make me co-host again?
Yes, sure.
Thank you. Okay, now I can share. All right, let me get the chat up. Okay, so everyone should be able to see my screen here with the with AFLOW-Online. Okay, so let's pick it up from where we were last time. We had our example part car here. This is an example of a carbide, which has a fixed carbon site here, and another site which is randomly occupied by metals. In this case, we have two metals here, okay, that are sitting on the same site, 50-50 occupied. And then we ran the POC module algorithm through the website here, and we see that we get the results. We get, okay, first and foremost, the algorithm needs to determine what is the proper supercell size for modeling the system. Okay, so in this case, because we only have two, we have a random site with two occupants. We see that the supercell size needs to be size 2. And then we can go ahead and actually calculate what the representative ordered structures are, and the algorithm will provide that for you. Okay, so where I'd like to begin here is with an exercise. We're going to stay together for this one. We're not going to go to our breakout rooms, but we're going to do an exercise here. What I would like you to do is, I would like you to, let's move this a little bit here. I'd like you to take these input part car, and right here on the web in this module, I'd like you to modify the part car to create a 5-metal carbide. So here we have a 2-metal carbide. You should change it to be a 5-metal carbide where it has one random site of carbon, a fixed site of carbon, and a random site of the metals with 5 metals that are equally represented. Keep in mind that the species has to be in order. And then when you create the structure, go ahead and run the POC algorithm and tell me how many ordered representative structures you find. Okay, so we'll give a few minutes. It would be great to see who is the first person who's able to provide the answer in the chat, or you're welcome to unmute and tell me what you find. Otherwise, we'll give a few minutes and see where people can get. Excellent. It looks like someone's already gotten to the answer. Khalid put forth the answer that there's 49 unique supercells. Great. Is that the unique structures we're looking for? Yes, the 49 structures. Yes, that's right. So, so Khalid, so let's see well, so the answer is correct. So I know that Khalid did it well. We're going to walk through how to do this together. Okay, so the part car is going to stay the same mostly up until about the lattice parameters. These are going to stay the same. That's fine. We're going to change the settings here because this is for 2-metal carbide and we're going to make it a 5-metal. So I'm just going to copy these lines, this section here, and I'm going to put 5, and they're going to be represented instead of 0.5, it's going to be 0.2, right? Because they're equally represented. There's 5 of them. And this section here is not too important. I mean, we can change these numbers here, but these are mostly comments. The only thing that AFLOW understands is the D here and the P here. Okay. So we're going to change the sites here. And we're going to put, okay. These are comments as well. We don't need to be too concerned with them, but I'm going to change them anyway. And then I'm just going to change the species here to be in order. So MO rather, B, TA, V, W. Okay, and I think that fixes everything. Yep. Okay. We're going to go to calculate POC structures, hit submit. Let's see what we get. Okay. So you see here, we get back a part car, which looks familiar. This is exactly what we're expecting. You see that it automatically changed the numbers here because this was understood by AFLOW. So, okay, so we get this structure back. You can see here, let me move this over. You can see here that we get the table. Instead of having just 2 lines, it went to 5 lines. So at 5 lines at a supercell size of 5, which is what we expect, we get we get an error of 0. See, the table's a little longer, but we effectively reduce down our error to 0. So that's great. So a supercell size of 5, and you can see here that it's going to calculate. Okay, so there are 5 H&F matrices, unique ones. So that's 5 different box shapes within which we can decorate the atoms. For a given box shape, there are 120 different ways of putting the atoms inside. Okay. And that gives us 600 different supercells that we need to explore. So of these 600, the UFF force field method determines that there are 49 that are unique. Okay, and they give you the energies here and the degeneracies. Take a look at the degeneracies. For all 49, well, for most of the 49, we see that there's all of them are 10, except for one, which has a degeneracy of 120. Okay, and that's what I was alluding to earlier. One of the structures may have a much larger degeneracy than the others, and that's structure bin 45. And then it prints out the unique structures here for you. So you get a list of all 49 here. Okay, so there are all the structures. All right, any questions about that? If not, we'll move on. Okay, so I'm going to stop sharing. I'm just going to share my PowerPoint here. Okay. Can everyone see the right presentation mode?
Yes.
Yes.
Perfect. Thank you. Okay, so let's pick it up with how to do these analysis. So I showed you how to interact with the POC module through the web application. But you can also interact with it through AFLOW. And I'm going to show you some of these commands, and we're going to play with how to create these structures. So my recommendation when you create a part car is that you always start by creating the parent structure first. Okay. So in this case, we've been looking at carbides, which have a rock salt structure. So the parent structure, as you remember from yesterday's lecture, it has this AFLOW prototype designation. Okay, 225, that's the space group for the rock salt structure. And then params equals -1. So here we have our typical rock salt structure, basically undecorated. Okay. Now, what I want to emphasize here, when we're going to build our POC structure, there's two different declarations that we're going to need to be aware of. So this structure has two different species, A and B, and it also happens to have two different sites. So the site positions, in this case, it has two different site positions, but it's possible that you have two species and let's say 4 positions, right? Where there's 2 positions of A and 2 positions of B. So keep in mind that distinction, the distinction between the number of species and the number of positions. In this case, they're equivalent, 2 and 2. So to construct the POC Params command, okay, so we're just going to build off the command we had earlier. So before we had AFLOW proto, we had this designation here for the prototype, the backbone structure. Now we're going to decorate it with the 5 metal carbides. So we have to put everything in alphabetic order. So C comes first, that's the carbon. Then we list the 5 metals. Okay. We have params equals -1 for the regard law. That's okay. Now we have to specify how we're going to decorate our structure here. Okay, so let's take a look. So position 0, we're going to specify it as a per positional designation. So for the first position, we're going to, we start with number 0, right, which is the first position. It's fully occupied, 1 times A, where A here refers to the first species here, which is carbon. Okay. Then we have an underscore and we specify the second position, which is position 1. And we do 0.2 times B separated by hyphens, 0.2 times C, 0.2 times D, 0.2 times E, and 0.2 times F. So those are the 5 metals. Okay, B, C, D, E, F. Okay. And it's equally occupied between all the 5 metals. Okay. So this is how we build our POC params. This is going to be the most difficult part. Well, let's not say difficult. It's the most technical aspect, let's say. So when we run this command, AFLOW will give us back what looks like it's going to be the part car. Okay, so it's a generalization of the postcar. And you can see here that this is exactly the structure we built in the web application. Okay, and it builds it for you automatically, specifying all of these parameters exactly. Okay. Okay, now what we can do is we can take the part car and we can pipe it back into AFLOW as an input to the -HNF command. And what it's going to do is it's going to show you all of that output that you saw on the web. And then you're going to see the table come up and it'll tell you the optimized HNF value is 5. This is equivalent to running the first button on the web application. Okay. If we run -HNF cell, this is the same as running the second web button, which gives us all 49 unique structures. So the HNF cell is going to actually do the calculation for you. You're going to run the calculation of which are the unique structures. And then it's going to enumerate those structures for you on the command line. Okay. Now, it will, so this is if you want to just get one structure and you want to play with it in the command line. If you want to build an aflow.in file for you to submit to the queue, for you to run this disordered system, you need to create an AFLOW-in. So we're going to change our proto command. We're going to keep it the same. All the other parameters, all the same. We're going to change proto to AFLOW proto, and we're going to add this generate AFLOW-in line so that it skips the checking of the pseudopotential files. And if you run it successfully, you're going to get an output that tells you that it created this directory structure. Okay. And so let's take a look at this directory structure. So what we have is it's going to create a directory called AFLOW data. That's where this AFLOW-in is going to sit inside. The first layer of this directory structure is the chemistry layer. Okay, so it's going to have a listing, a string, which has the different pseudopotentials that you use. So this is carbon, molybdenum, PV. This refers to the particular pseudopotential for VAST, NB, SV, et cetera, Paul, PBE. This is the default for VAST for AFLOW. So this is the chemistry layer. Okay, these are all the different components. It's really just focused in on this particular part here. The second layer is the structural layer. So how do we how do we build the structure given that chemistry? So you see that the first piece of it here is the parent structure. Okay, this is the rock salt structure. And then it's going to append to it a colon and add POC and then the POC Params command that you specified. Okay. So that's the directory structure that we're going to build. And then inside of that inner layer, you're going to get an AFLOW in. Okay, let's actually run that together. So I'm going to share my screen. My full desktop. And I'm actually going to copy this command. You should be able to download the PDF and copy the command as I'm doing right now in my PowerPoint. We're going to go to the cluster here. Oh, it's going to ask me to connect. 1 second. Am I connected to the? Yeah, I'm still connected. 1 second. Pull up the password. Oh. 1 second. Okay, so here we are. Okay, so we're going to, if we start off at home, I want you to CD into AFLOW exercises, day 3. Okay, and then you're going to go inside of 06 POC. Okay, let's go inside of Scratch. Scratch. I'm going to give everyone a minute to navigate there. Okay, so I have the command copied here. I'm going to paste it. So, because it's very long, let's do a paste. Okay. And I'm going to do edit, paste. Okay. We're going to hit run. And if everything runs successful, you get this output here. Okay, where you get this tree structure, AFLOW data, then you get the chemistry, the chemistry layer, then you get the structural layer. If you go inside those 3 layers, you're going to see an AFLOW in. So I'm going to gedit AFLOW in. I'm going to open up the AFLOW in and we're going to take a look inside. It should look like a typical AFLOW in. There's a lot of settings. We're going to scroll down. These are all basically defaults. And you're going to see that instead, usually what we have here is VASP mode, postcar, explicit. This is now, you see here that this is a POC structure. You can see that the POC mode explicit, and you have all of the part car settings that we specified earlier. And you also have AFLOW-POCC calculate, okay, telling you to calculate the structure. Let's see, where should I change? Maybe write the command. Absolutely. Let me put that in the chat for sure. Right there for you. Okay. And we also have this AFLOW-POCC calc. No problem. Okay. So, so we're going to close this out. Close. Don't close without saving. Okay. So, what we're going to run here is we're going to do AFLOW --run --j generate AFLOW in only. Put that in the chat too. So inside of this directory where we have the part car, this layer here is the part car layer. Let me make this bigger. I'm going to, and I need to paste it in. Okay. We're going to run AFLOW run generate only. Not too much. I could have typed that out. We're going to hit enter. And you see that you get, oh, wow, it's very fast. So what you see here is, I'm going to try to scroll up so you see everything. Okay, so we get a usual AFLOW analysis. So it's going to figure out what the parent structure is, and it's going to go ahead and calculate the symmetry of that. That's what all this output is giving you here. You get the point group crystal. We went through some of this stuff yesterday. But okay, so after all the symmetry information, you're just going to start to see the POC analysis. Ooh, okay, it's really very fast. Okay, so what you should see is the usual table, okay, where it figures out what the optimal size of the supercell needs to be to get zero error. And then it shows you that there are 120 different permutations. So there's 600 different supercells to enumerate. Then it goes ahead and calculates which ones are unique, determines that there are 49 unique, returns back all the energy information, and then it's going to, let me show you. I'm going to run ls. It created 49 subdirectories. So we have this A1 POC 01, 02, all the way up to 49. Okay, so those are the 49 unique structures that now you need to go into VASP and run. So in order to do that, we're not going to run it with VASP today, but what you need to do is you need to go in. Basically, each one of these A runs is going to be an individual VASP run. So you can parallelize all 49 of these runs. If you have a nice big cluster with at least 49 nodes, you're going to go into A run POC 01. Okay. You now get an AFLOW in here, which can be run with VASP. Okay, so if you look inside of this AFLOW, and this is just an example, I'm going to scroll down and show you. You can just follow with me on the screen. You're going to see that you get VASP postcar mode explicit. Okay, so now this is a VASP postcar. You can take this AFLOW in and you can run it. So if we had VASP on the machine, you would do AFLOW minus run, and you would specify, you would have to set up your machine and set up the configuration for, letting AFLOW know where your VASP binary is, et cetera, et cetera. But that AFLOW in gives you the all of the parameters and the settings you need to run VASP for all 49 of these 49 of these unique structures. So presumably, we anticipate that we're going to run VASP for all 49 of these structures. We're going to get the energies of these structures, and then we can do the post-processing there. Okay, so we're going to do the post-processing a little later. But for right now, I just want to emphasize that you're going to get 49 unique structures. You run VASP on all 49 of those structures in parallel. And then once you're done running VASP on all 49 of those structures, then you do the post-processing. So in order to do that, well, we'll get to it later, but you're going to move your lock file to lock.run or something like that. And then you're going to run AFLOW run again in this directory. And AFLOW is going to go in, try to see if the directories are created. And then if it has the necessary VASP output files that it needs to read in to get the properties, to do the analysis, et cetera, et cetera, et cetera, et cetera. Okay, that's the idea. That's where we're going. Let's keep going here. Okay, so an important distinction here. So P versus S. Remember, I want you to keep in mind that there's positions and then there's species. So we've been doing it based on positions, but where will S be useful in terms of specifying the POC parameters? Let's imagine that instead of using the rock salt structure, we instead want to use as our parent structure this material here. So I'm going to show you what this looks like. Okay, so this is cementite, and it's got a lot of Wyckoff positions. If we do VASP output, you're going to see that we actually have, okay, this is a binary. Okay, it has carbon and iron, but it has 16 different positions. Okay, so if I have to specify the partial occupancy for all 16 positions, you can imagine that this command is going to explode in length. It's going to get very big. But if instead I want to specify the partial occupancy based by groups of positions, so the first 4 are carbon and the next 12 are iron. Maybe I want to specify the partial occupancy based on species. Okay, so let's take a look at that. So again, we have, this is the structure here. We have position 0, position 4, position 15. Okay. 0, 15, remember, because we started 0. But we have species 0 and species 1 here. Okay. So building this command where we want to specify, maybe I tell you that the carbon are going to be all fixed like in the rock salt, and we're going to decorate the iron site with 5 metals. To do that would make a very, very long command because you have to go from P0 to P15. Instead, we can truncate that by specifying it by S. So I'm going to say basically that all of the carbon positions here are specified by this parameter here, which is 1 times A. So they're all fully occupied. And then species 1, where the iron sits, I'm going to randomly occupy with the various metals here. This command is nearly identical to the one I showed you earlier, except instead of S, instead of P, I have S. And I can change the prototype here. So we have a change of the prototype and then a change of S, and that's it. That's the only change we have from the other one. So you can see how convenient it's going to be to specify for some structures which have a lot of positions to specify for species versus position. Okay, and we get a part car, very long part car, but this is what we get ultimately. Okay. We have some nice high throughput commands. Okay, so this is similar to the convex hull commands I showed you earlier, where you can actually create many AFLOW-ins at one time. Okay, so in the study that Professor Cudarolo referred to in his keynote speech, keynote talk about where we studied the various 5 metal carbides, there were 56 combinations, right? Because he in his talk, I don't know if he mentioned this detail or not, but in the talk, we basically had a choice of 8 different refractory metals that we were going to combine with carbon to make 5 metal carbides. So if you take 8, choose 5, you get 56 combinations. Turns out that we can actually create all of those AFLOW-ins with a single command. So I'm gonna first I'm gonna paste this into the chat. You have it, this nice long command, and I'm going to show you that what the various pieces are of this command. So first I'm going to come out of here, and I'm going to, just because I want to show you a count, I'm going to delete the AFLOW data. We're actually going to end up recreating that directory in a second, but here's what we're going to do. I'm going to paste that command right here. And then we're going to talk about what's going on. Okay, so I'm going to paste it, and let me show you what's going on. So what we have is we have C, which is fixed. Okay, so C sits by itself. And remember that previously we separated all the species by colons. So we have C, colon, and then we're going to have all of the metals from which we want to choose for the first site, comma separated. And then we have a colon. And then this specifies site 2, site 3, site 4, and site 5. So what's going on here? What is AFLOW going to do? AFLOW is going to take the carbon, and it's going to take 1 from this set. So it's going to pick hafnium first. Then it's going to pick 1 from this set. It's going to try to pick hafnium, but hafnium is not a unique it's not going to be unique in terms of generating all the combinations. So it's going to skip hafnium, go to molybdenum. It's going to pick 1 from this set. So instead of hafnium, it's going to pick niobium, and it's going to go on so on and so on and so on. So it's going to generate all of the combinations going through all of those different possibilities at each site. And so we're going to see that AFLOW is going to do that, and it's going to, so I'm going to hit run here. 1 second. Okay. So you see here that it's, okay, so it's creating some structures. 1 second. It's very fast. But you see a lot of them are neglected because we end up getting something like carbon, hafnium, and that doesn't make a 5 metal carbide. It's going to make a 4 metal carbide. So it skips that combination, and it's going to go through all of the possibilities, trying to create all of them. And then at the end, you're going to have what you should have. So what I'm going to do is I'm going to do find here by name AFLOW in, and I'm going to count the word count. I get 56 different AFLOW ins, which is exactly what we expect from the combinatorics. So if we go inside of the AFLOW in, you'll see that we have 56 different chemical combinations here. Okay. And each one of these has its own structure layer. I'll show you what it looks like inside, but it's the same as what we expect. You know, the parent structure and then the Poc Params. Okay. And then inside of there, we have the AFLOW in. We're going to want to go into every one of these 56 subdirectories and run AFLOW run to create the 49 unique structures for each one of these chemical combinations, making something on the order of 2,000 AFLOW runs to actually run with VASP. Okay. So that's one example of a high throughput command. Another one that you have accessible. Let me come out of here. I'll post this in the chat. Saeed, I'm not sure. I'd have to take a look. We can explore that when we go into the subgroups, but you should, did anyone else get an error when they tried to run the command? You may want to check that there are no weird spaces when you did the copy paste into the command. Yeah, go ahead. Thank you, Dr. Esters. Let me paste this command in for everyone else. So this is the command we're going to run now. This is for different Poc Params. So what we're going to do is, I'm going to paste this here. Edit, paste. Okay, so what's going on here? I can actually do different Poc Params, comma separated. So here we have one specification, which is I want to take the first site and fully occupy it with the first occupant, which is carbon, and then do a 50-50 of B and D. So this is going to be a 2-metal carbide. I do a comma and I can create another structure, which is a, oh, interesting. This is going to be a, okay, so this is going to have fit. Okay, so for the first site, let's break this up. For the first site, we're going to have 50% occupied between A and 50% occupied between C. So C and N, that's going to give me a 2 anion structure. So it's a carbon nitride. And then the first site is going to be 50-50 split between the two metals. So in the one specification, I have a 2-metal carbide. And then in the second specification, I have a 2-metal carbon nitride. Okay. So you can do that with one command, comma separated. You can append as much as you want, all the different commas there, and it'll create all those AFLOW ins for you. Okay. All right, so we have a number of exercises. We have a good amount of time too. So these exercises, especially the third one here, this is going to take a while. You're going to want to, go through this with your subgroup helper there. But basically, okay, so let's go through the exercises. Okay, so you're first going to create a part car for this ternary system. I give you the rock salt prototype label. So 201, instead of the AB225, that designation of prototype, you can just plug in 201. This is an alias for that structure. Okay, and this alias 201 is for the rock salt structure, and then you can specify the species and the Poc Params as normal. That's the first question. Second question is create a part car for this other ternary system, sulfur selenide, zinc sulfur selenide system. I give you the prototype label to word site structure, and you're going to want to try using S instead of P here. Okay. The third example is to create an AFLOW in files for this binary system, iron copper, spanning all of these concentrations with one command. And you're going to want to do them with label BCC and FCC. You can remember the prototype can also be comma separate. So you can do BCC comma FCC and then do the full span of concentrations with the POC params. And for each one of these different part cars, tell me how many representative structures you get for each. So let's go ahead and break up into our breakout rooms. I'm going to stop sharing my screen. We're going to take a look at what we have with the breakout rooms. Okay, I'll start assigning some people different places. Guys, we'll give everyone another 5 minutes. Okay, I think we have almost everyone back. 1 second. Looks like we have a question. Corey, I missed it. Can you explain again or point to the slide that shows what the top 3 numbers are in the part card? Sure. Well, here, 1 second. Well, I'm happy to explain it. So I will share my screen in 1 second. Okay. Let's share the screen. Okay. So here on slide 20, you'll see that we have the 3 numbers here. These are the site and stoichiometry tolerances. Okay. So what you're going to want to pay attention to is that there's 2 numbers here. And for the purposes of this lecture, we're going to keep these. We're going to keep these. 1 second. Let me just close the. We're going to keep these numbers fixed to 0.001 because basically we want to emulate. We really want to emulate the stoichiometry exactly. But I think it becomes very clear when you look at the table what these numbers mean. Okay, so let me go to a table where it's a little easier to read. One second. Okay. So here we have the table for the 5-metal carbide. Move this over. And we have, by the way, everyone can see my screen, correct? I just want to make sure. If I get a thumbs up, you guys can see my screen here.
Yes.
Okay, perfect. Okay, so the error that's important to look at is, so you see that you get the site error and the stoic error. Okay, the site error is one parameter that looks at the average errors. Well, actually, it's the maximum error that you would see or per site that you miss when you model the structure at exactly that particular supercell size. So remember, I walked through this one by one. So I said, if we want to model our structure as supercell size 1, then that means that there's only going to be one site within which I'm going to be able to occupy one of the 5 metals. So the error should be on the order of what I'm missing with respect to the not including the other metals. So you see here that there's 0.2 error in the site because I'm missing the stoichiometry. I'm missing the metals, the other metals in that position. So the Stoic error is the error of the overall composition of this structure. So by picking one metal, I have a carbon and one metal. So it's C. Let's say I pick hafnium. So carbon, hafnium. So I've missed the 0.2 of the molybdenum, of the vanadium, of all the other metals. And so that's going to give me a Stoic error of 0.5 here. Okay. Does that make sense? So we want to look at these last numbers and we want to make sure that the tolerance values that we give it, the error needs to be below that tolerance for the stoichiometric tolerance and the site tolerance. One second. That makes sense. Great. Okay, good to hear. All right, that's a great question. All right, so let's go a bit through the exercises. One second. Okay, there's a really a nice opportunity for everyone to build their own part car using the command line here. So here we are in Scratch, and you're going to want to make a part car. Make this a little smaller for magnesium zinc oxide. Okay, we have the prototype there, and there's no params. So we're going to want to type first. I always advise always create the backbone structure first. So AFLOW minus proto equals 201. So that gives us our rock salt structure. I always know that it's a rock salt primitive structure because I get zeros along the diagonal here for the lattice.
Corey,
Okay.
sorry to interrupt. Maybe could you make a font a bit bigger?
Yeah, let me do that. Zoom in.
There's also another question in the chat, by the way.
Oh, great. Thank you. Question. Is there a way to generate also the magnetic moment string in the generated structure? It's a great question. Automatically, the answer is no, not as of right now. You would have to generate the string. It's actually, I'm not even sure it would be possible to do it from the part car level. I guess you can, because somehow we would need to figure out how to propagate that information on a per species basis, per species or per position. But I would say, well, okay, at least for now, you cannot do it from the command line. But of course, within the AFLOW-in, you can go in and change the VASP force setting, and you can give whatever magnetic moment you want, for instance, for VASP, and I'm not sure what it would be for quantum espresso, etc. So as of right now, the answer is we don't have that, but that would be a very nice feature to add, especially as we start to explore magnetic materials. Okay, so we've created our background prototype. We see that we have 2 species and 2 sites. So I'm going to specify the Poc params based on the per position, because that's always easier. So let's put, the first thing to do first is to put all the species and put them in alphabetic order. So it's MGOZN. Okay. Then we're going to do the Poc params. Okay. And now, so we want first, I'm going to remember that, okay, well, a hint that's useful. I didn't tell you where the oxygen is going to sit, but it turns out it doesn't matter because the A and B sites are equivalent in the rock salt structure. Okay, so I'm going to put the oxygen atom on the first site just to fix that, and then we can focus on the disordered site second. So I do P0 1 times B, right, where B is this site. It's the second site. Okay. Next, let's go to the disordered site. So P1, 0.25 times A, and then hyphen 0.25 times C. And that should give us the part car we need. Okay. Any questions on how to design the command for building this part car? Nope. Now, the last question asks us how many representative structures we get for each. So I'm going to hit up arrow. So I get back my command, my original command, and I'm going to take this input and bring it back inside of AFLOW to do the analysis. So I'm going to do a pipe AFLOW minus HNF cell. Okay. That is the command. I can try to copy this command into the chat. Let me try that. Yeah, I can. All right. So there's the command there. And then I'm going to hit enter. And it's going to run that analysis. And we see that we get all the representative structures here. We should get, I think it's 7. Yes, we get 7 of them. So we get 7 structures here. Okay. The number is also written here in green, calculated 7 unique structures. All right. Any questions on that exercise? Great. All right. Second exercise is very similar. We basically get a different prototype. So we do AFLOW minus proto equals 219, right? Because I gave you the word site prototype here. Easy. So let's check out the structure first. We always want to take a look. Now you see there are 2 species, but 4 positions, right? So by specifying the partial occupancy here, I could either do it per position or in an easier sense per species. So I'm going to put the zinc in the first site, okay, as I did earlier. Well, first, we need to put all the species. So we put them in alphabetic order. Sulfur, selenium, zinc. Now we need to design our Poc Params. Okay, so I'm going to do S0. So that's going to cover these 2 sites here. And I want to fix the zinc 1 times C, because that's the zinc site here. Okay. Then I'm going to do underscore S1, and I want to do 0.75 times B, and then 0.25 times C. Is that right? I might have done it backwards. Oh, times A, I'm sorry. So 0.75 times B, right? Because sulfur has 0.25, and that is the second position here. And then 0.25 times A. Okay. We hit enter. We can check out if we have the right part car here. So we see that we have these 2 positions here that are equivalent. These 2 positions that are equivalent. We have sulfur, which is 0.25, selenium, which is 0.75, and then zinc, which is fully occupied. Okay. So that's how we design that command. And I can do AFLOW minus HNF cell. I'm going to copy this, put it to the chat. Okay. And if I hit enter, we're going to get a bunch of structures. I believe the answer was, if we scroll up, I hope that gives me the opportunity. Oh, yeah. See here, we get 27 unique structures. Okay. So that's the answer there. Okay, for the last one is the most challenging. It's not really challenging, it's a little tedious. Okay. So AFLOW, we have BCC and FCC label. Now, the important thing here is that actually we can't really test it with all of the commas and everything, because to create these combinations, we're really creating AFLOW ins. You can't do it with the proto command. So we're going to have to do AFLOW proto equals BCC comma FCC. Okay. That's the first thing. But what I want to do first is just show you. You can just follow it with me on the screen. AFLOW proto equals BCC. I just want to take a look at the structure. So we know that the BCC structure has 1 site and it's 1 species, and FCC is the same. You'll see that in a second. It's the same, it's just got a different lattice. Okay, so you see here that FCC. Oh, 1 second. Interesting. BCC and FCC. Okay. All right. This looks like a slightly different. Interesting. Okay, well, FCC is here. Okay, so this is the FCC structure. Okay, so we're gonna build. We're gonna build the command, and I need to do it with AFLOW Proto. So I'm gonna do BCC comma FCC colon. Now I want to put the species there in alphabetic order. So copper and iron. Okay. And then the piece that's tedious is the Poc Params. Okay. So for the first one, we want to do 0.1 and 0.9. So since we only have one site, we can do P0. That's very simple. So P0 dash 0.01 times A, 0.9 times B. Okay. And then we're basically going to do this over and over again, but changing the 0.1 and the 0.9 to 0.2 and 0.8 and so on and so forth. So P0, 0.2 times A, 0.8 times B, and so on and so forth. Okay. So I'm just going to hit enter here. So I just want to show you that it'll create the 4 variants here. Okay, we do because we have BCC, FCC, and then the 2 Poc Params that we have, and we could span the whole set here with one command. Okay, so that's how we do it. And you'll see that if you look inside, here, you see that I get BCC, that's the parent structure, and then the Poc Params designation afterwards. All right. Any questions on how to do that? If not, we will move on to the slides. I'm going to stop sharing. I'll share my slides, and then we'll pick it up from there. Okay, can everyone see my screen and I'm in the right mode? Perfect. Okay, so we got a question earlier about whether we've tested this analysis with the properties of the material. How well does this algorithm or methodology work in terms of modeling the properties of the disordered material? So we've done these tests for a number of different properties. The first one I'm going to show you is we did this for zinc sulfur selenide system, this cacalgenide system. We've been playing with this system in the exercises. This system turns out to be, it has a band gap, but it has an interesting phenomenon with the band gap where if you look at how the band gap changes as a function of concentration. So if I go from zinc sulfur to zinc selenide and I look at all the compositions in the middle, as I vary the composition of the selenium and the sulfur, I'm going to get this quadratic relationship here, this bowing, it's called optical bowing relationship between the band gap and the concentration. Okay, so it's been observed in a number of different experiments. The calculated results with AFLOW-POCC is the one that is shown here in the blue. And you see that the blue emulates the experiment very well. Now, there's an important note here. If you remember from, well, we didn't get to discuss this, but density functional theory tends to, it underestimates the band gap. So what I did is I did a rigid shift of the band gap for the calculated results. And you see that if I just shift my axes, I end up getting the relationship very well, right? I'm not getting the exact values correctly because the DFT has problems with the band gap, but the relationship, this bowing relationship, is captured very well by POC. We can also look at the band gap relationship versus concentration for this magnesium zinc oxide system. It's well known that by doping zinc oxide with magnesium that we really expand the band gap. So in the short range from zinc oxide to about 0.5 of concentration of magnesium, we have this word site structure and the relationship looks mostly linear, okay, for the experiment. And then when you cross over to the rock salt, there's a phase transition here. We go from wort-site to rock salt. The relationship looks a little more quadratic. Okay. And you can see that the calculated results actually emulates this very well. It really models the system very well. We can look at the ensemble average density of states. We did this for the zinc chalcogenide and the magnesium zinc oxide. Now, what's interesting for this system is that we can actually look at, using the POC algorithm, how the band gap changes. How is it that the band gap changes? Is the valence band being pushed back? Is the conduction band, is it shrinking? What's going on here? So it's really obvious, I think, for the magnesium zinc oxide system. You can see here that the conduction band's really being pushed back with respect to the density of states here. So these were all done with POC calculations, and you can see very nicely how the density of state changes as a function of the concentration of magnesium. We've also looked at ensemble average magnetic properties. Now, magnetism is very difficult to do with DFT. And so it's important that you're very careful with these analyses. But what we did is we looked at this iron copper system. We know that iron is magnetized, copper is not. And so we look at the magnetic moment as a function of concentration. As we increase copper, we expect the magnetic moment to drop. And it turns out that even through a phase transition, this relationship is mostly linear. And you can see that our calculated results emulate that of the experiment very well. Okay, we've even looked at the density of states here. We know that basically the concept here is that at the Fermi energy, as the system becomes more non-magnetic, the density of states should drop at the Fermi level. Okay, and so you can see here that at 0.2 concentration copper, the density of states is much higher than that of the 0.8, where we're mostly copper. Okay, so we can recover these sort of results from that we would expect from the literature using our POC model here. We have an important metric here. So in all of our analysis, we've been assuming that, if we want to model a 2-metal carbide, we only need a supercell size of 2 to emulate the stoichiometry exactly. However, you can go to HNF4. So you can build a bigger supercell that's going to satisfy the stoichiometry exactly. It's going to match it. And you're going to get a bigger set of the ensemble, and the structures themselves are also larger. So what I have plotted here is starting from 2, which is what we need to model the magnesium 0.5, zinc 0.5 oxygen structure, and the same for the zinc chalcogenide. We need exactly a supercell size of 2 to model the stoichiometry exactly. But what if we increase the supercell size beyond that? So by increasing the supercell size, we're increasing the cost of the calculation and hopefully the accuracy as well. And that's exactly what we see here. We see that the error, I lost the y-axis here, but this is the error of the band gap. The error of the band gap decreases as you increase the supercell size beyond that which is required. We did a similar calculation for the magnetic moments here. What I did here is I focused on this BCC structure, and the magenta here are bigger supercell calculations using the AFLOW-POCC algorithm. And you can see here that it better approaches the experimental values. So that's exactly what we expect with a methodology that is growing in cost. We expect that it also hopefully grows in accuracy. Okay, so now let's talk about what we can do with AFLOW-POCC in terms of thermodynamic analysis. So what I have here are these 3 systems that I've been talking about: the zinc chalcogenide, the magnesium zinc oxide system, and the iron copper system. What if I wanted to plot the enthalpy of mixing for these systems? Remember, it's a little different than the enthalpy of formation. Enthalpy of formation is always with respect to the components. Here, it's going to be with respect to the precursors. So we expect that at 0, we're going to have, at the pure component edges, we're going to have an enthalpy of mixing of 0. And then because these are disordered structures, the enthalpy of mixing should be positive, okay, because these will be realized with a bit of entropy and temperature. And so what we end up seeing here is the only thing I want you to focus on are the orders of magnitude of the numbers here. So you can see here that the enthalpy of mixing is pretty small for the zinc chalcogенide. It gets bigger for the magnesium zinc oxide system, and even bigger still for the iron copper system. And what's interesting is that what we know from experiment is that the compositions here for the zinc chalcogенide, as you go from pure selenium or pure sulfur rather to pure selenium in that particular site, all of these concentrations are realizable in experiment. So at room temperature experiments, we can actually realize these materials. They are actually stable, and they're stabilized, of course, by the entropy of the system. However, if we go to the magnesium zinc oxide system, there are ranges within which we cannot access certain compositions because they phase separate. So here in the orange, I show that in the bulk, we cannot, the bulk is actually the lighter orange. For the bulk material, we actually cannot realize a big range of compositions here. We have the edges here, that's fine. But inside of this orange range, this light orange range, if we try to synthesize the bulk material here, the material actually phase separates. Okay, so it doesn't form a solid solution. If you try to do it with thin films, there's actually a tighter region of immiscibility. Okay, and that's that dark red here. Now, the same can be said for the iron copper system where the enthalpies of mixing are much larger. Actually, the full range of compositions are not realizable. As soon as you start to dope with copper, it's going to phase separate. It really doesn't want to be in this mixture here. And so what we see here is that as the enthalpies of mixing are increasing, so is the immiscibility of the system. And that's exactly what we see reflected in the numbers here from POC. Okay. So one of the things that we want to do is we actually want to parameterize entropy. Entropy as a quantity is very difficult to calculate. But if there's a descriptor that we can develop that would scale or parameterize the entropy in some fashion, that's going to be very useful for us. So remember in the beginning of the talk, I talked about glasses. So we have certain compositions that are going to tend to want to form glasses better. They're going to want to form a glass. And this quantity of the ability to form a glass is called the glass forming ability. That's the obvious name. So we want to develop a descriptor that would tell us that for a certain composition, how likely is this composition to form a glass? How likely is it? We've created an equivalent concept in the high entropy field, which is called the entropy forming ability. And that is the tendency for the system, the composition, to want to form a high entropy phase. Okay, so let's talk about these concepts. The first one is a sort of a historical, chronological story, if you will. I'm going to show you how we've developed this for the glass and then how we translated this to the high entropy alloys. So here we have a copper zirconium system. And this is a known metallic glass. And what we're going to look at are the energies here at the 50-50 concentration. And what you see here is that there's a very tight cluster of structures that are very similar in energy. Okay, that's the idea that I want you to focus on. All these structures are very distinct. You can see here that in this cluster here, we have structures that look like this, structures that look like this. They have different lattices, different arrangement of the atoms. They all have the same concentration, and they're all very similar in energy. We can quantify this concept of similarity or clustering of very similar energetic structures by looking at what's called the thermodynamic density of states. So you can see here that I have a tight cluster here. So I get this histogram, this big bar here. And then as I go up, there's bigger spread here. So the cluster is smaller here. This bar here is smaller. So this is really like the density of states in the electronic fashion, but this is for this is looking at it from the perspective of the energy of distinct structures. This is the thermodynamic density of state. So the idea here, the descriptor is we're going to look at the width of this distribution. If the distribution is very tight, then that describes that scenario I talked about earlier, where we have a lot of distinct structures that are all very energetically similar. Okay. And this is actually going to quantify what's called the glass forming ability. What is the idea here? The idea here is that if we have a lot of structures that are very different, but they're very similar in energy, then there's a lot of confusion in the system as it's nucleating. So as the system is trying to form a solid, it needs to decide, am I going to go to this structure, which structure do I pick? And if they're all very similar energetically, there's a lot of confusion. The analogy I use here is imagine that you go to the ice cream store and let's say you're a big chocolate lover, and you walk into the ice cream store and there's two flavors of ice cream. There's vanilla and chocolate. Okay, it's going to be very simple for you to make a decision of which ice cream to pick. So you're going to pick the chocolate. If you walk into the next ice cream store and there turns out to be 50 different flavors, half of which are varieties of chocolate, which one are you going to pick? And the answer is you may walk out of the ice cream store with more than one flavor. And that's what happens here in glasses. So instead of picking one ordered structure, it's going to be sort of an ensemble of these structures, which is what we get. This confusion structurally it comes out in the form of making a glass. So this confusion that we get from this distribution, this is actually what quantifies this glass forming ability. We created a very similar concept, an analogous concept in the high entropy field, where we look at the distribution of these POC structures, the energetic distribution of these POC structures, which are all derivative structures of that parent structure, that parent lattice. And we're looking to quantify what is the accessibility of the random decorations. If all of these decorations are very similar in energy, you're going to expect that the system is going to want to form a solid solution where these sites are randomly occupied, because all of these different sites, site occupations are very similar energetically. And it's exactly what we did. When in this study of the metal carbides, we looked at 5 metal carbide systems. Again, we had 8 refractory metals to choose from, and we wanted to form 5 metal carbides. So there were 56 different combinations. And we sorted them by our respective EFA descriptor, which I'll talk about what it is in a second, but it's that idea, keep in mind that idea of sorting it by how similar they are energetically. And the ones that had the highest entropy forming ability actually formed solid solutions. And we were able to experimentally verify this. So here we have some of this data from experiment, and you can see that from the EDS data that the material, the composition is very uniform. Okay, the metals are really equally distributed throughout the crystal. So what is this EFA parameter? Okay, remember we're doing this analysis in 6 dimensions. So these are the energies. So remember, we had 49 different configurations. We did this example earlier. We had these 49 different configurations. Let's create the thermodynamic density of states. Let's look at that distribution of energies. And what we did is we sorted them and we looked at what the standard deviation of that distribution is. Okay. The EFA is the inverse of that standard deviation. It's very simple. It's a very simple concept. So you can see here, as the sigma increases, as the standard deviation increases, the EFA is going to decrease. And that EFA decreasing results in phase separation, as opposed to forming a solid solution. Okay. So the natural question is, does this EFA parameter, other than dictating synthesizability, does it actually correlate with a concept that we can relate in experiment? And so we look at this Bragg relation here. This is a relationship that we can get from the XRD data. And and there are various quantities here, but the quantity to focus on is this epsilon here. This epsilon has to do with the peak width. When you look at the XRD data, it is associated with the chemical inhomogeneity, which results in this peak width expanding when you're looking at the X-ray diffraction data. So this epsilon here quantifies chemical inhomogeneity, and we plot it against the inverse of the EFA. And you can see that we get this very nice relationship here. So these materials here at the bottom in the green, they form homogeneous single phase systems. And those in the red at the top here, they form multi-phase systems. So this EFA descriptor very easily determines, we can just draw a line right here and say that anything in the middle there, and we could say that anything below it, roughly speaking, should be a single phase, and anything above it should phase decompose. Let's focus on this material here, which is the one that has the highest EFA. In a lot of ways, this material defies intuition. So keep in mind, remember, we built these structures earlier. They have a rock salt parent structure base, parent structure. And intuitively, if we look at some of the other compositions here, so let's focus on the other two, the next nearest two, which are these hafnium base, high entropy carbides. From the perspective of an experimentalist, the formation of these solid solutions, there's some intuition there, okay? Because if you look at all of the precursors, hafnium carbide, niobium carbide, tantalum carbide, titanium carbide, all of these precursors, they are also all rock salt structures. However, the highest EFA material, this molybdenum-based high entropy alloy, this has two non-rock salt precursors. Here we have this alpha phase for the molybdenum carbide. It's MO2C. It's not MOC, it's MO2C. And we have a tungsten carbide here, which is W2C. It also turns out that this material has a very high distance from the hull. Remember, I told you earlier that systems that are very high, that are very far from the hull, they're going to be metastable. And if they're really, really far, they're not going to want to form. But the point here is that there is so much entropy in this system that the system is really entropy. It has so much disorder that it overcomes this enthalpic penalty, which is this very high distance to the hull. So there's so much disorder that it overcomes this issue with the enthalpic penalty. And from the epsilon parameter that we had earlier, the highest EFA also tells us that it's the most homogeneous system. Another point I want to make is that we looked at the hardness values for these materials, and roughly speaking, let's say if I asked you, I said, hey, what is the hardness value for this high entropy system? One measure of that, or one way to predict it, is to look at the hardness values for all the precursors. So hafnium carbide, niobium carbide, tantalum carbide, and take the average. Okay, this is called the rule of mixtures. We see that some of these materials have as much as 50% hardness increases over the average. So the fact that they form these solid solutions actually contributes to their hardness and makes them even harder than what we expect from them on average, just on their composition. So disorder is also playing a role in increasing the hardness of these materials. This is what makes them so attractive. All right, so we're gonna wrap up now with the last exercise for the session. And so this is the post-processing. We're going to go into our small groups and we're going to run the post-processing command. You're going to see it's actually very simple. And so you're going to really let the algorithm run. You might ask some questions, and then you can actually plot the density of states, both against the orbitals and the species. So let's go ahead and break up and go for the final time today into our breakout rooms, and we're going to run these commands together. Okay. Let me stop sharing. I think the breakout rooms are mostly set, right? Yep. Okay, let's go. All right, let's wait for everyone to come back, and then we'll go through the answers very quick. Oh, it looks like everybody's back. Okay, let's go through these exercises. It should be pretty simple. Basically, in the small group, the majority of the time should have been spent just waiting for the calculation to run. Let me share my screen because I'm going to share my results. Okay. Okay, so the first thing is you should have noticed that once you run the post-processing, you're going to get several new files. The first file you're going to notice that you get is this AFLOW-POCC.out file. This is the final results file. We'll go through what that looks like in a second. Then you get a whole list of DOS cars, which are the density of states files for VASP. It's written in that format, but you're going to get the density of states at various temperature snapshots. So by default, it scans from 0 to 2,400 Kelvin. And based on these snapshots, we can actually plot what the density of states is. So the two commands you would have run together in your breakout room is, you should have run this command. Let me expand this because it's a long, very long command. Well, not the command's not very long. The command line prompt is. The first command you should have run was aflow plot DOS equals dot. So the dot is for plotting the density of states of the values that are in the current directory. And then you can do projection equals orbitals, which is the default. So if I don't specify projection, then it's by default orbital. And then otherwise you do species. Okay, so if you do orbitals, you're going to get these different files, which is the density of states as projected along the orbital. So let's take a look at what that looks like. So I get all these new PDFs here. So if I look at the orbital projected density of states, this is at 0 Kelvin. You get this nice picture here. Okay, so you can see the contributions SPD. And then we look at it at 300, at 600. You can see how that density of states changes as a function of temperature. If you do projection equals species, you can see the breakup as a function of the species. So you get the same density of states plot, but now you have contributions from carbon, from molybdenum, niobium, tantalum, vanadium, and tungsten. And you can see how that changes as a function of temperature. Okay. So those plots are pretty simple. Any questions on how to plot that? Okay. All right, so the last thing I'm going to show, and then we'll wrap up for the day, is the AFLOW-POCC.out. And you can just follow with me on the screen here. There's a lot of data that's written in here. It's broken up by temperature snapshots. So the first temperature snapshots are the properties that are true at all temperatures. Okay, so first it gives you the degeneracy values for each of these the derivative structures. And you remember that for all the derivative structures, they all had a degeneracy of 10, with the exception of one, which had 120. It's the last one here. It gives you the enthalpy per atom of the supercell. So these are all of these DFT calculations that you did the 49. It'll give you what those enthalpy values are. That's the HI from our slides. And it actually tells you which one is the ground state. This one has the lowest enthalpy of the whole set. And finally, at the bottom, you're going to get the ensemble average enthalpy, which is called enthalpy mix per atom. And then you get the entropy forming ability. Okay, so 117. And then for all of the temperatures from 0 to 2,400 in increments of 300, it's going to print out how the probabilities look for each temperature snapshot. And you're going to see that they're all 0 at 0 temperature. They're all 0 with the exception of the ground state. So that was A run 27, and that has probability of 1. And that's why all the properties at 0 temperature are going to be skewed toward the properties of the ground state system. And then if you keep going, you're going to get the probabilities start to change as you incorporate temperature. Okay, now that you're introducing temperature, there's going to be more disorder. Any questions here? This is the full set of results, and I'm happy to take questions. You're now all experts in running the module, so feel free to send me a note if you have any questions. I'll put my email here in the chat, but otherwise I think we're going to wrap up for today. So thank you very much for your time, and I'm always here to help, so feel free to shoot me an email. Thank you very much. Have a good one.